In 1999, two researchers at Harvard University asked volunteers to watch a short video of 6 people passing basketballs and count how many times the players in white shirts made a pass. The task required genuine concentration. The groups moved constantly, the passes happened fast, and the count required sustained attention. Halfway through the video, a person in a full gorilla suit walked to the center of the screen, faced the camera, beat its chest, and walked off. The gorilla was on screen for approximately 9 seconds. When asked afterward, roughly half of the participants said they had not seen the gorilla, not that they hadn't paid attention to the gorilla, not that they dismissed it as unimportant. They had genuinely failed to perceive it. The gorilla had been there, visible, center frame, for 9 full seconds, and their brains had not registered it. Daniel Simons and Christopher Chabris ran this experiment as a modern refinement of earlier work by psychologist Ulrich Neisser, who had first demonstrated the basic principle in the 1970s. Neisser showed that people selectively failed to notice events in a visual scene when their attention was already committed to something else. Simons and Chabris sharpened the design and gave the phenomenon its formal name, inattentional blindness. The definition is precise. Inattentional blindness is the failure to notice a clearly visible stimulus when attention is directed elsewhere, not because the stimulus is hidden, not because the visual system malfunctions, but because attention was occupied and never got to it. The finding seems impossible until you understand what attention actually is. Human visual attention is not a floodlight that illuminates everything in view. It is a spotlight, narrow, movable, and capable of illuminating only a small portion of your visual field with genuine clarity at any given moment. The rest of the field, the peripheral regions, the elements you're not focused on, is processed by the visual system at a far lower level of detail. You have a sense of your surroundings, but you have not actually examined them. And when something new appears in the space you're not examining, your brain does not generate an alert. The gorilla doesn't trigger your awareness because your awareness is fully deployed elsewhere. This isn't a malfunction. It is how attention was built to work. Sustained, focused attention is metabolically expensive and cognitively demanding. The brain allocates it selectively based on task demands, and it commits hard to whatever task is currently active. That commitment is useful in most contexts. It's what allows you to read a book in a noisy room, follow a single conversation at a crowded party, or thread a needle under poor light. The cost of that useful narrowing is that things outside the attended region can pass completely unnoticed, regardless of their physical salience or their absolute size in your visual field. What makes this feel impossible is that we have a powerful and persistent sense of seeing our entire visual environment. You feel like you're taking in the whole room when you walk into it. But this sense of comprehensive visual awareness is largely a construction, a feeling of knowing rather than an actual full-resolution scan of everything present. Your peripheral vision provides low-resolution information about surrounding objects, and your brain fills in the rest using expectation and prior knowledge, generating a subjective sense of presence that is far more complete than the actual data you've processed. You are not seeing the room. You're having a feeling of seeing the room. The difference between those two things is where inattentional blindness lives. Simons later ran a key variation of the gorilla study that revealed just how deep the effect actually goes. He showed a new group of participants the same video and told them explicitly to watch for the gorilla. Almost all of them saw it, but in the process, a majority failed to notice that the curtain in the background had changed color partway through the video. Knowing to look for one unexpected thing did not protect them from missing a different unexpected thing. Attention had been redirected, but it remained just as narrow. This connected to a parallel line of research on what's called change blindness, a related phenomenon that Simons explored with Daniel Levin in a famous experiment conducted outside the lab. A researcher stopped pedestrians on a campus and asked for directions. While the pedestrian was answering, 2 workers carrying a door walked between them, briefly interrupting the interaction. When the door passed, the researcher had been replaced by a different person, different height, different hair, different clothing. Approximately half of the participants simply continued giving directions to the new stranger without noticing the swap had occurred. The change had happened completely and directly right in front of them. Their eyes had been open all along. But the brief interruption had been enough to prevent the kind of direct comparison that would have made the change obvious. The practical consequences of inattentional blindness extend far beyond laboratory experiments, and they are not trivial. Traffic safety research has documented that drivers talking on hands-free phones, not handheld, just in active conversation, fail to process a significant portion of their visual environment, missing pedestrians, traffic signals, and other vehicles at rates substantially higher than non-distracted drivers. The hands are on the wheel. The eyes are open and forward. But attention is partially allocated to the conversation, and portions of the visual field go entirely unprocessed. Eye tracking studies have confirmed what seems improbable. A person could be looking directly at an object with their gaze center on it for a measurable interval and still not consciously perceive it if their attentional resources are committed elsewhere. The eyes land on it. The brain doesn't record it. Medical imaging provides one of the most striking professional examples. In 2013, Simons and colleagues ran a study in which radiologists, experts who spend their careers scanning images for abnormalities, were given chest scans to examine for lung nodules. The researchers had superimposed an image of a small gorilla, 48 times larger than the average nodule, onto one of the slides. 83% of the radiologists did not report seeing the gorilla, even though eye-tracking data confirmed they had looked directly at it. They were in expert mode, searching for a specific type of finding, and the gorilla, despite being enormous by the standards of what they were trained to find, fell outside the category of thing they were actively looking for. This is perhaps the most uncomfortable version of the finding. Expertise doesn't protect you from inattentional blindness. In some cases, expertise makes it worse, because expert performance involves increasingly automated, structured, category-driven perception. You learn what to look for, and what to look for is not the same as everything that is there. What helps is not simply trying harder to see. It is disrupting the assumption that you already are. Checklists, structured search protocols, deliberate interruptions that force attention back to a wider scan, and explicitly asking what else might be here that I haven't looked for. These are interventions that make inattentional blindness less likely not by expanding attention, but by redirecting it before fixation sets in. Subscribe, because every single week we show you one more thing your brain is doing quietly in the background while you assume it's doing something else entirely.